At this point in your mathematical education, you may have experience with the natural base e simply as it relates to something such as compound interest or radioactive decay. In this section, we're going to examine the calculus definition of the natural base. The value of e is defined to be the limit as x approaches infinity of 1 plus 1 over x raised to the x power. Now, with all of our new skills, we're actually going to prove this limit. So let's suppose that this limit L is equal to the limit as x approaches infinity of 1 plus 1 over x raised to the x power. Our goal in the proof is to demonstrate that the value of this limit L is e. So we know we can take the natural log of both sides. This is getting to be a little bit routine by now. It's pretty predictable when you practice. I'm going to switch the limit operator and the outside function natural log. I bet you know what comes next, right? We're going to move the exponent on the argument of the logarithm down to the left as a coefficient. Now, looking at what we have here on this side of the limit, we've got two factors. We have our x factor and we have our natural log function. As x approaches infinity, well, x approaches infinity, right? And as x approaches infinity, this term approaches 0, so the value of this function goes to natural log of 1 or 0. So we have the form infinity times 0. Now that is not a green light for L'Hopital's rule, so we are going to have to manipulate this expression. Remember, infinity times 0, not necessarily 0. Sometimes yes, sometimes not so much. So we're going to take this factor x and we're going to invert it and put it in the denominator. That way the expression that we're dealing with here is equivalent to the expression on the line previous to this one, and now we have an indeterminate form we can use. As x approaches infinity, the natural log function goes to 0, and as x approaches infinity, the denominator goes to 0. That's the green light for L'Hopital's rule. So we will individually differentiate that numerator and denominator, starting with the log in the top. So I'm going to darken my main fraction bar here. Okay, so I can see the individual derivatives of the original numerator and denominator. So differentiating the function in the numerator, we're going to take the argument of that logarithm in the denominator, and we'll have the derivative of that argument in the numerator. Then looking at the function 1 over x in the denominator, when we differentiate it, we end up with negative 1 over x squared. Let's go ahead and correct this complex fraction. I'm going to multiply this time by negative x squared, so I can cancel those negatives at the same time. So the x squared cancels here, and the negatives cancel. X squareds cancel here, and the negatives cancel as well. So let's see if we can decipher what we have here. We have natural log of L on the left, limit x approaching infinity. What's left of that numerator is 1. 1 plus 1 over x, and a 1 in the other denominator. So that is as simple as it's going to go. Now, as x approaches infinity, this term approaches 0. So it looks like the value of that infinite limit on the right is 1. Now, solving for the original limit L, which we were trying to find by converting to exponential form, L equals e to the first, or more simply, L equals e. We can say, therefore, the three little dots mean therefore, the original limit that we were calculating, the limit as x approaches infinity of 1 plus 1 over x raised to the x power equals this very extremely important number e. Now, maybe this will shed some light on what you learned about compound interest. The formula for compound interest looks something like this. The amount accumulated value in account is the principal times 1 plus the rate divided by the number of times interest is compounded per year time raised to the exponent of n times t, where t is time in years. Maybe that's a familiar formula to you. Well, you may have also learned about continuous interest. With compound interest, you have distinct compounding periods, right? If n is equal to 2, you're looking at interest being compounded twice per year. If n is equal to 12, you gain interest in your account 12 times per year. And you discover quickly that the higher the n value, the more number of times interest is compounded per year, the better the investment it is. So what happens as n approaches infinity? Let's keep increasing those compounding periods. If you do that, you end up with something called continuous interest. And maybe you learned in a college algebra class the formula for continuous interest is PERT. That's what I like to call it anyway. What you can see here is as n approaches infinity, then you're approaching this exponential function. And it is related to this limit that we just proved. So again, E is used in finance. E is used in calculating the half-lives of radioactive elements in chemistry. E is used in modeling population growth. E is used in even figuring out the half-life of medicine in your bloodstream. E is an extremely important number. In fact, I even have a Bible study, if you're interested, on E in the Bible. It's related to life. It is a very fascinating number. But what you need to know for this class is we now have a calculus definition of E. E is based on this limit at infinity, which we were able to prove with L'Hopital's rule there in the mix. Now, if I change it just a little bit, if we look at the limit as x approaches infinity of 1 plus a over x raised to the x power, clearly we're just changing this number up here in the numerator. This is e to the first power, therefore this is e to the a power. Hope you found that interesting, and great news, we have completed all the information for Chapter 7.